course of recent climate change are mounting. We are here to discuss this further. Bert Metz will give a brief introduction on the subject, followed by the other speakers.
Okay. The highlight of my story about the climate change risk and what we can do about it is as follows. Climate change risks are very serious. And is there any microphone here? Okay. And have the potential to undermine our economic growth and development. Action is very urgent. There is absolutely no time to waste. The good news is, technically and economically, it's possible to control this problem and to stabilize greenhouse gases in the atmosphere at a low level. But in order to do that, we need policies to turn the opportunities into real action and give people and businesses the right incentives. And last but not least, developing countries have to play a major role in solving this problem while pursuing their own development objectives. And therefore, the Copenhagen Agreement that is being negotiated right now on climate change would have to provide the means to developing countries to make their contribution. So these are the highlights. Let me zoom into a few points. Just to give you a flavor, if you look at the top yellow line, that's the low-level stabilization that gives us, say, a world which is not warmer than about 2 degrees above what it used to be pre-industrial. But that means our emissions globally have to peak, say, by 2015, or maybe in the best possible situation, 2020. And if it would take us longer than that, we're quickly moving to a world that's not 2 degrees warmer, but 3 degrees warmer, but a lot more in negative impacts. We do have the opportunities. This is an assessment from IPCC across all of the economic sectors of what we can do, how much we can reduce, and what the costs are. The basic message is there's lots of opportunities at reasonable cost, but the top bar here, the lighter blue, is the share of the potential that is in developing countries. So we not only have to do this, we have to do it in developing countries which have not exactly the right conditions at the moment to play their role. If you look at it globally and you look at the right-hand picture for a 450 CO2 equivalent stabilization, that's the 2-degree world. We can get there by a combination of all of the technical opportunities there are. It's efficiency, it's nuclear, it's renewables, it's biofuels, it's CO2 capture and storage, it's fuel switch, it's also planting forests, sinks, and it's non-CO2 gases, methane, fluorinated gases. So it's basically everything we have to apply. And this means we are facing a huge transition of our energy system from a predominantly fossil fuel, you see on the left hand, to a system which is run on a combination of renewable sources, bioenergy, nuclear, solar, wind, plus fossil combined with CO2 capture and storage, which basically turns that into clean fossil. The costs are not trivial. These are large operations, but if you express it in terms, and look at the right-hand side, if you express it in terms of the amount of money you have to invest in these technologies, in the case we look at, the top blue one on the right-hand side goes up to sort of 2% of our global GDP. So it's still a big amount of money, but it's not an excessive amount. But that's roughly what it would take. It will build up from now till 2030 to that level. Macroeconomically, the question is often how does that affect our economic growth? Macroeconomically, it will have some effect. If you look at the row that says 445 to 535, that is basically a 2 to 2.5 degree world. And you look at the far right, you see the reduction in annual growth rates, economic growth rates, is in the order of 0.1 percentage point. So instead of an economic growth of 2%, you go to 1.9 or 1.8. Now, if you're in a recession, that's sort of certainly not good news, but overall, over a long period of time, these are manageable costs. And there are benefits in addition, not only the benefit of avoiding all the damages, but also avoiding air pollution, which is normally going hand in hand with making fossil fuel cleaner, and you save a lot of health cost. You have improved energy security if you use energy efficiently. If you use your local renewable solar and wind resources, you reduce your import dependency. You can create additional employment. Renewable energy systems require more people per kilowatt hour than a coal plant. So it has a lot of positive economic things. And then on the policy issues are just one example of what is an effective policy to turn these opportunities into action. One is the reduction of fossil fuel subsidies. The world is still full of subsidizing coal, oil, and to the extent of more than 200 billion euros a year. If we would take those subsidies away and use part of that to subsidize the renewable energy forms, it would be economically better, and we would have a clear incentive to move to other sources of energy supply. The other good example is how do you stimulate the building of wind farms and solar plants. You do that very effectively by a so-called feed-in tariff. Companies get a guaranteed price for 20 years, which is higher than what the regular price is, and on that basis they get the business incentives to build these things. It works very effectively. So the last point is how do we make it possible for developing countries to play their role? And basically we have to face that. For developing countries, such a thing as a feed-in tariff might be difficult. They have to give a subsidy of maybe 10 cents per kilowatt hour, and that would have to be absorbed by the economy and by the people who are relatively poor. So it's often difficult for developing countries to do that on their own without support from the outside. So basically the message is there needs to be significant amounts of money made available to developing countries. And the order of magnitude of that is 65 to 100 billion euros per year for the coming 10 years. That covers not only these actions of shifting from fossil to renewable energy, it also covers adaptation cost. The climate will change further, there will be more negative impacts, and particularly poor countries are affected and need to protect themselves and adjust their economic development. So that adds up to significant amounts. They are large in, say, in absolute terms. In terms of a percentage of global GDP, they are relatively small. And certainly compared to global investments, they're even smaller, in the order of a few percent or less than 1% actually. But I mean, ensuring that this amount of money is becoming available for developing countries, that's one of the big challenges of the Copenhagen conference that is running at the end of the year, which is the culmination of the ongoing climate change negotiations. So I think I should leave it with that.
Thank you. Pierre, what is your view on this?
Well, I think we had a very good summary of the various challenges that we are facing. I'm working for an oil company, so you know that I could be seen as part of the bad guys. What was interesting in this session is that you will see that with Andy. We will show some example of carbon capture, which is one of the very promising technologies that we can use for decreasing the impact of carbon on this planet. You will see that most of this technology is actually coming from oil and gas exploration. So I think it's a way to change completely it's a way to change the image of oil companies, and it's also a way to change the way the technology is used. So I would say it's, for me, it's a very good perspective. It's a very good news. Again, you will have more details in the summary of Andy's presentation.
Who would like to respond?
I don't know, shall we give our presentations now? Is that the best way? Okay, I'm going to give a presentation just focusing in on some of the issues surrounding carbon capture and storage. So if I can just...
I have to tell this thing that it should release. It doesn't want to do it, so put it next to me.
Yeah.
It is very clear that mitigation must be approached by a portfolio approach. This is one of the key messages of the latest IPCC report. What comes with this, if you go into closer economic analysis, is a tremendous increase in the share of investments of global GDP that have to flow into these technologies. For example, our institution calculated that you have to crank up the share of GDP that has to be invested into renewables by at least an order of magnitude. And it's now a question of insurance policy of society. The larger the portfolio is of mitigation options, the more you secure yourself against surprises. So carbon capture and sequestration is also an important member of this portfolio, and we will see now Andy's presentation. Please go ahead.
Okay, then we'll just show a few slides about the concept of carbon capture and storage. Essentially, as you see at the top, we extract the CO2 from the flue gases of a fossil fuel powered power station, and then we transport it via a pipeline and then inject it into the subsurface, into a subsurface reservoir, typically at depths of 1,000 meters or more. When we're thinking of large-scale storage, the amounts of storage that we'll need to actually have an effect on climate mitigation, we're talking of storing hundreds or even thousands of millions of tons of CO2 in the subsurface. It's a buoyant fluid, and so to make sure that these storage sites will actually perform as we expect and we hope, then we're going to have to monitor them. And basically, the key aims of monitoring really are to make sure that the sites will comply with the regulatory regimes. These regimes are still under development, but there is now an EC directive on storage, and basically it requires that a site operator will have to demonstrate that he understands how the site is working, that it's performing as expected, and also that it will continue to perform as predicted over the long term, in fact over the very long term, in other words for thousands or even tens of thousands of years. So this is quite a challenging problem, and you know, basically we aim to use the monitoring to demonstrate this, and there are lots of monitoring tools out there. Lots of universities, lots of companies have got lots of different technologies. Some are focused in the deep subsurface, shown in this cross section where the CO2 is moving in the rocks, and some are focused perhaps on identifying possible leaks at the subsurface. At the surface. Perhaps the key requirement of demonstrating that you understand how a storage site is actually working is deep focus monitoring. I'll just show a quick example from Sleipner. At Sleipner, CO2 has been injected since 1996. It's been separated out from the natural gas, and about 1 million tons of CO2 there are injected per year, with about 11 million tons currently in situ. This is not as much as a power station will produce, but is of the same order. And basically, the underground distribution and movement of the CO2 is being monitored using a technique known as time-lapse seismic, which was originally developed by the oil industry for oil production. And basically, on the right, at the bottom right, you see what we call a seismic cube. This is essentially a continuous volume of data, which is an image of the subsurface. Right at the top, we have the sea. Then we have the bright orange reflection is the seabed, and down towards the bottom of the cube is the actual image of the CO2 in the subsurface at a depth of between 800 and 1,000 meters below the seabed. And basically we can use this time-lapse seismic. Here we have images showing a vertical section through the cube and also a horizontal plan through the cube to show us exactly where the CO2 is moving from 1994, which was prior to injection, up to 2006. And basically from the plan view we can see how far the CO2 is spread in terms of scale. It's about 3.5 kilometers now from the southern end of the plume to the northern end of the plume. If we now look to some other monitoring aims, we also need to essentially show that sites aren't leaking, and if they are leaking, albeit perhaps in a minor way, then we need to quantify the amount of leakage in order to conform to national inventory requirements and also emissions accounting such as the EU ETS. And also monitoring obviously has to take into account health and safety issues. So basically for these aims we're really looking at shallow monitoring. Basically the deep focused technologies such as the seismic shown on the left give you a very continuous coverage of the subsurface. Where shallow monitoring is a little bit more challenging. We can make point measurements as is shown in the bottom right there. This is someone doing soil gas measurements at an injection project in Canada. But basically the issue with point measurements is that it may be that there are quite large amounts of CO2 escaping in between the points which would not be detected. And so current research is focused on developing new technologies whereby we actually do continuous aerial measurements using mobile measurement systems such as a buggy-mounted infrared radar system. Overall, our conclusions, therefore, is that the monitoring are essentially aimed at complying with regulatory requirements, and the key challenge is to develop site-specific, cost-effective strategies. Points perhaps well worth making is that it's better to do the work properly at the start. So if you characterize your storage site properly before injecting, then it's much more likely that the monitoring will be able to verify that it's working properly.
Thank you. Hans, would you like to continue?
Yes, someone can put this on the computer. And while we put it on the computer, I think I would like to make some comment on carbon capture and storage, which is...
You get here onto this seat.
Okay. Which is certainly a technology which we will need for the next decades. There is no question, and it's no competition in my view with the renewable techniques. However, it's also obvious that this is only a transitional technology. For example, in Germany we have reservoirs for about 30 years of carbon dioxide at present power plant capacity, and after that there's no storage place left. And I would expect this to be similar for many other places. But during this period of time in between, at least this gives us time to build up the capacity on renewable technologies. The German Aerospace Center has during the previous 10 years done some major studies on the present and future electricity requirements of 50 countries in Europe, the Middle East and in North Africa. And we have analyzed the demand, the present power plant capacity, and we have analyzed all renewable energy sources that are available. And the clear outcome of this is that the solar energy is by far the largest resource that we have. If we look at the countries in the Middle East, North Africa and Europe, we have about 150 times more economically achievable electricity from solar power plants, then we need electricity at the moment. And if I can just show you a picture, and can we just take the next one? This picture here shows you the size of a solar power plant in the Sahara Desert that we would need to supply the whole electricity demand of the world, of Europe or of Germany. That means 1% of the area of the Sahara would be enough to supply the complete electricity demand of the world. These solar power plants are not the solar cells that we are used to have on our roofs here, where we have 1 or 5 or 10 square meters of solar collectors, photovoltaic collectors. These are solar power plants. And if we can just have one more, please. A look here. Basically, they are a combination of conventional power plants like gas, oil, coal, or nuclear power plants, the same cycles with steam turbines, and solar plants where the sunshine is focused in large mirrors to produce heat at high temperature. Basically, we have large mirrors, say 6 meters diameter, 150 meters long, which focus the sunshine like a lens does. And with this, then, so concentrated solar radiation, we can generate steam, which then drives a conventional steam turbine. These power plants are not new. There are some examples which have been in operation for the last 25 years in California. They work reliable. They can be combined with heat storage to produce 24 hours per day of electricity. We are talking at large-scale electricity, not at 1 or 2 kilowatts. We are talking at hundreds of megawatts in one power plant, which will then be fed into the national grid. And I just want to show you some examples of power plants which have gone into operation in the last 2 years. This is a power plant or 2 power plants close to Seville in Spain. One with 10 megawatt and the other with 20 megawatt. The next one is a power plant also in the south of Spain with 50 megawatts, which has gone in operation just a month ago. And the exciting one here is this is already equipped with large heat storage, so they can operate up to 20 hours per day in summer in Spain, producing 50 megawatt for the national grid. This is the electricity you need for a town with 200,000 inhabitants. And the third one is also one in Spain, which has gone in operation just 2 weeks ago. It's a smaller one. It's only 2 megawatt, but it's a new technology with a huge potential for cost saving. If we look worldwide, then we can see that worldwide at the moment there are building and planning activities in the order of 10,000 megawatt or 10 gigawatt capacity of solar thermal power plants, which are already in an advanced stage of planning or even building, some of them already operating. And once these plants are in operation, the cost for electricity from solar thermal power plants will be comparable with the cost from gas or oil plants or coal plants together with carbon capture and storage. We of course are aware that those power plants make only sense in parts of this planet where sun is abundant, not in Austria, not in Germany. So these plants will be built in the sunbelt of the world, but it is possible to link these power plants, for example, from North Africa with Central Europe by electricity lines, so-called high voltage direct current lines, where instead of alternating current, you have direct current. This is again established technology. There are hundreds of those lines already in operation worldwide. There's one in China, 2,000 kilometers, 6.4 gigawatt capacity, 6.4 gigawatt. So these are like 6 large nuclear power plants in one line transferred over 2,000 kilometers with a loss of only 7% over the whole length. And with these power lines, the electricity will be supplied from North Africa to Europe, and we would envisage that by 2050 about 15% of the European electricity supply would come from such power plants, to add to the electricity from renewable sources which we have in Europe, like photovoltaics, wind, geothermal, wave, and also to add to electricity from fossil and from nuclear power plants. Thank you.
Thank you, Hans. Could you also explain something about the Fresnel technology that you are currently using?
Well, the Fresnel technology was actually the technology which was just shown on the third of these examples here. It's just a special arrangement of mirrors focusing on a pipe in which water is evaporated. You can either do this with large curved mirrors, or you can do it with a number of flat mirrors where each flat mirror is then adjusted. But the effect is more or less the same. They have different advantages and different disadvantages.
Thanks. Now the next speaker is Hermann.
Thank you. So all of these talks have shown that in principle mitigation is possible. The technologies are there, the costs are moderately low. The question is now how to incentivize the cost optimal path. It's very important that investors get the right signals that long-term investments into low-carbon technologies will pay off in the long run. So for that reason, it would be very helpful if long-term expectations towards binding mitigation targets could be stabilized beyond 2020. At the moment, the legal framework that we see in the European trading system has a horizon of 2020, but for many very important investments, it would be very helpful if the horizon would be clear until at least 2050. So this is one of the key requirements for any legal framework that should incentivize mitigation in a very cost-efficient way. I'm very thankful for the presentations we have had in this union session. It was the first union session at EGU on mitigation, and we had the major technologies tackled, renewables and in particular solar thermal as well as carbon capture and sequestration. We think that it would be very wise, now speaking for European climate policy, to have such an investment stream that we have a choice as a society in 2020, so that we have built up massive capacities in terms of renewables, but also have demonstration plans for CCS, so that we ensure ourselves against surprises. And then society has a choice. It may go with one of the two or with both, and it's very advantageous of very high advantage to feed in investments into both channels at the moment. Yeah, that's the key message that come out of economic analysis set up in such a way that you also ensure yourself against surprises. It's not only about cost optimization in a perfect world. This is the first iteration of economic analysis. This is usually done, but it's also important to ensure yourself as a society against surprises. And here a broad folder of mitigation options is very helpful, of course. Thanks a lot.
Thank you. We still have a few minutes left for questions. Who would like to start?
I'm Liz Callagher from Environmental Research Web. This is a question for anybody who'd like to answer. What do you think is the best way for the Copenhagen Agreement to proceed?
Let me give it a first shot. It's very important to get a clear signal about the long-term direction that countries want to take. So that's the point Hermann made. You have industry needs a long-term perspective. So and you don't know what you have to do in the short term if you don't know where you want to be in 40 years later. So something of an indicative target for 2050 is an important element, and countries in the world should agree on that. Second is deep reductions committed by industrialized countries, and then a system where developing countries will also undertake things supported by major financial and technical support. Those are basically the key things. I mean, behind that is a lot of detail about, I should make one exception, institutions. Having the right institutions that can evolve over time to make this all work together and report and decide on what next needs to be done, etc. Machinery on the finance, how it's going to be collected and dispersed, etc. And then behind that there's a lot of detail about technology issues, about patent rights, about how to deal with forest in particular, and etc., etc.
Well, let me get away from the policy side and say something for the technical side, which I think is absolutely a requirement. And if we want to get a high percentage of renewable energies in our electricity supply, and I think I want to make this completely independent on what type of source of electricity. This could be wind and photovoltaic, solar thermal, all the others. What we need is an electricity grid which can cope with this. This is the requirement for all the renewables. And this is something which we don't have at the moment. That means we need an electricity grid which on the one hand side will have lower electrical losses. So this could be this electricity backbone with high voltage direct current. But we will also need an intelligent grid which can cope with the fluctuations which we will have and which can balance out the demand and supply from different sources, rather than having a local electricity supply where you have a power plant just for a town and then another one for another town, and maybe a little bit of exchange between the two.
Scientists and engineers are always very quick to come up with technological solutions, and we've seen that these are indeed very promising. But what else needs to be done? Hermann, could you elaborate on this a bit more?
Well, there's always the question about sufficiency in the room if we talk about mitigation, and in fact for the OECD this might be an interesting option, but I don't think that for developing countries this is a topic at the moment. They are very suspicious us talking about sufficiency while we have accumulated a very high standard of living. It's very interesting to see the maps of accumulated capital as against the accumulated amount of emissions over the last 100 years, and it's a one-to-one correspondence almost. So we have all built this capital being built up and have emitted a lot in the past, whereas now the developing countries would like to get their share, and for that reason I think sufficiency discussions for them are very difficult. The protocols that Bert talked about will be very important, that there is a technology transfer to developing countries, there is an adaptation fund made up maybe from auctioning permission rights in terms of CO2 permissions that could then feed into an adaptation fund that we help them adapt to climatic change that is unavoidable even if we mitigate very strongly. There's already 0.6 degree warming in the pipeline, even if we froze greenhouse gas concentrations in the atmosphere today. Then it would be very helpful to have in the end a global cap and trade system with some rules, sort of per capita rights at one point in time, for example 2050, so that there's a notion of justice on top of the discussion of technological solutions. If you have found a way to solve the climate problem on a global level in terms of cutting mitigations, nothing is said who will cut those. So this is a different discussion, a different dimension to the problem that has to be tackled in international negotiations, and now it's a very difficult, also scientific, social scientific thing to find a stable coalition on mitigation internationally. So how to stabilize, for example, an international cap and trade system. We have the European trade system and there are other trade systems emerging worldwide, and it's an emerging branch of social science and economics at the moment in terms of game theory, how you can make up protocols, international protocols to link those cap and trade systems. If we do not get the big solution at once in Copenhagen, to build on the existing islands of trade systems that run the mitigations down. This is a very promising Plan B approach, if you like, that's also researched on in our institute. But also sufficiency, of course, especially in the OECD, should be on the agenda. Is it really necessary to keep certain things going on that do not really increase the well-being of human beings? And there's a gray area between sufficiency and economic theory that could be utilized. Economic theory indicates that, for example, efficiency improvement in terms of buildings is already paying off even if we did not have a climate policy. It would just pay off because energy prices will rise. But people are not doing it. For some reason, they are not investing into their buildings, and the house owners are not, even the house owners are not investing because this time scale at which you get the return is too long, 20 years or even longer. So here society has to move on. It's inconvenient in that sense. I could call it also a sort of sufficiency that I'm willing to undertake painful renovations at my building. It's not convenient to do this. It's even if it pays off after 20 years, but you are aware of the impact of energy loss even to the environment. And also to the national economy. The national economies are losing a lot because of just energy loss through ill-insulated buildings. And therefore, a common understanding what are key mechanisms that are even cost efficient in the long run would be very helpful here. So the idea is that in the end, and also industry has an important part to play here, the investments we are talking about are strong. For example, making up a supergrid that Hans was talking about. A supergrid means there's a whole switch, a collective investment into many branches in industry that have to fit together. And for an individual company, it's very difficult, it's very risky to undertake. Sometimes it's very risky to undertake such an investment because the whole supply chain may have to be changed. And building the understanding of the future of a low-carbon society, how this may function, this is a collective act, a collective stabilization of expectations, if you like. We need science for this, we need industry for this, we need the whole society for this. That they understand there is a parallel world, a better world with less emissions that is possible, and we get together in understanding how this could work. And therefore, union sessions like this, I think, are very important to disseminate the knowledge that is necessary to a wider audience.
Hans, you were shaking your head.
Well, yes. First of all, I found it amusing when you said that scientists are always quick to come up with a solution. We have been working on this for 30 years with a capacity of 70 people.
But with
So
very good
this is a relatively long time already, and it finally comes to fruition. Now the other thing is, I don't think they're as complicated as the previous speaker maybe made it. I think like a supergrid or high voltage direct current grid, you can install this without directly affecting an individual plant or the individual person. It's like building a motorway. It doesn't affect the traffic on the streets of the city. And this is how one has to look at it. I also think that one should not just limit the discussion to climate change and CO2 emissions. We also have to look at resources. Our gas and oil resources are limited, there is no question. We have to look at it at the costs and the whole economy, because as we move on with increasing the contribution of renewables to our supply, they will become less expensive than the conventional energy supply. We are every year doing a scenario for the German government, which is called the German lead scenario for the introduction of renewables into the German economy. And this shows that if we reach our climate targets and at the same time restructure our electricity, mobility and heating infrastructure, we will break even as a society in 2025 to 2030, and after that the economy will even save money in comparison to the business as usual strategy. And yes, there will be investment required for this. At the moment, this investment will peak in 2015 at some 7 billion euro per year, and after that will go down again. We are looking at a cost per household in Germany, typically in the order of a few hundred euros per year. I think this is possible, and this is not even that painful.
So it can be done. Well, we've reached the end of this session. One more question?
My name is Patrick Judin, Swiss Broadcasting Corporation. Kind of like a skeptical question. Mr. Metz, I guess it was you who said that one of the requirements is that industry has a investment security for the next 30 to 50 years. When was the last time any industry had investment security for that period? Maybe the, I don't know, nuclear industry or fusion research, but who else?
No, I didn't intend to say that industry needs 30, 50 year security, but they need sort of to be pretty sure that this is where the world wants to go. If they want to invest in new products that would have to come online, say in 10 years from now, they don't want that investment to be wasted. So if it comes to investments, a 10, 20-year period is probably what they need. It's the way these feed-in tariffs work. They give certainty for 20 years. From an investment point of view, that's probably enough if you specifically invest in a concrete installation. But more broadly, in terms of further developments of new technologies, a broader vision is very welcome.
Pierre, what's the industry viewpoint?
I would be tempted to not to give an industry point to answer your question, just a personal comment. This is a scientific conference, right? So we talk about new technology, new equipment, new investments, that is fine. But personally, I don't believe that the society or this planet will solve the global climate issue without a change in our daily behavior, right? So this is, of course, beyond the scope of this conference. Here we are talking about human science or social science, even though society was mentioned several times by Hermann, but I want to make sure that everybody understands that whatever the new technology are, whatever the new investment, whatever the new equipment are, at the end of the day, I think one of the key issues is that are we capable of changing our daily behavior? And this is an open question. And it is really relevant for each of us.
Thank you.
Can I say one or two words about that?
Closing comments then, we have to stop.
There are attempts to quantify how much can you obtain with behavioral change. I mean, not just going back to the Stone Age, of course, but maintaining the sort of level of comfort we have, but by changing our behavior, you basically can get 10% more of reductions by doing that, but it's not of the order of the technologies that we need. Technologies, by the way, and behavior go together. You can make it easier for people to change their behavior if there is a bus coming to your house that brings you to the place you want to be. If there's no bus coming, then behavioral change doesn't make much sense.
Thank you very much for coming and for speaking this afternoon. This was the last EGU 2009 conference, Carbon Constrained Future. Thanks.